All right.
I'd like to join other speakers in thanking the organizers for organizing such a wonderful conference and for the opportunity to speak here. So I'm going to talk in a very basic way about some counting problems that arise in the study of n equals 4 string vacuum. There will be a lot of review in what I say, but to the extent that something new appears, it's based on joint work with a student in the Stanford Math Department, Arnav Tripathi, who is graduating and joining Harvard in mathematics. Better?
Yeah.
Okay. So I'll be reporting on two different projects, both counting objects in these vacua with 16 supercharges. And the canonical examples of such compactifications of string theory that I have in mind would be heterotic strings on a torus like T6, or type 2 strings on K3 times T2. Now, this may seem like a peculiar and very specific class of problems. My interest comes from sort of two sources of deeper motivation, which I'll barely be able to touch on today. Okay, first of all, I think I'm not alone in believing this, that our current way of specifying or formulating string vacua is quite primitive. We sort of use either two-dimensional world sheet CFT, or sometimes we use supergravity solutions. And these are both beautiful techniques with wide ranges of applicability. But it seems to me that sort of alternative formulations, perhaps using either auxiliary geometric objects associated to the vacuum or deep governing symmetries, could also be useful. And just to make sure this isn't too abstract, here are some examples of what I have in mind. In studying two-dimensional conformal field theory, one could, of course, start with a Lagrangian. Here's a Lagrangian for a scalar field with some phi to the k potential. And that's one description of the K theory in the minimal series of two-dimensional CFTs. But you can also, of course, consider 2D CFTs much more abstractly in terms of Virasoro representations, where the theory is specified completely by a list of primary fields, some conformal dimensions, and structure constants. And for many purposes, the algebraic view has turned out to be more powerful than the view based on Lagrangians. A second example arises in four-dimensional n equals 2 gauge theory. Again, the conventional view would be to take the list of fields in n equals 2 multiplets, write a Yang-Mills action with an f mu nu squared term and its completion with the scalars and fermions, and then study that directly. But of course, it's been clear for the last 20 years that considerations of some abstract auxiliary geometric object, the Seiberg-Witten curve, can often be a more powerful tool in analyzing at least aspects of these theories. Okay, now, so one good place to look for such structures in the more complicated context of string theory would be in the sort of simplest, most unique solutions that are available. And these are, for many purposes, vacua with lots of supersymmetry. And today I'll confine myself to theories with 16 supercharges. Okay, here's a second motivation. Some of the simplest objects that appear in these theories, the BPS states, those that preserve some fraction of the supersymmetry, have very nice counting functions if you just try to make a function that will count the number of such objects. And both the BPS states and their counting functions have been implicated in various interesting ways in study of string vacua. For instance, in n equals 2 compactifications, it was proposed years ago by Harvey and Moore that hints of an underlying generalized Kac-Moody algebra would appear in expanding the prepotential at low energies at one loop in the heterotic string, and studying it as an expansion in positive roots of an underlying large dimensional symmetry algebra, by analogy with the expansion in positive roots of the loop correction to conventional n equals 2 field theory. And then, of course, there is the role of BPS states in the string theory accounting of black hole entropy, where one starts at weak coupling with a BPS set of d-branes of various sorts. A famous example is d1, d5, continues in the coupling constant until the thing turns into a black hole, and uses index theorems to predict the entropy of the resulting black holes with great success. So the plan of the talk will be to start with black hole counting functions. Only at the end of that will I get to some of the deeper motivations that I had for studying these functions, and then to close with something much more speculative. So you can construct a wide class of 5-dimensional charged rotating black holes as follows, as explained to us by BMPV. Consider type 2 strings on K3 times S1. Consider a configuration that carries at least the following charges. There will be some number of 1 branes wrapping the S1 and 5 branes wrapping the entire compact geometry. We'll call that product of those numbers n, and we'll relate it to a number QE in this way. In addition, There can be momentum on the circle, which we'll call qm squared. And there could be some angular momentum in the transverse dimensions that are non-compact, which we've called here JL, and which we denote by QE dot QM. The QE, QM, and their dot product are the U-duality invariants of the U-duality group of this kind of compactification. Now, the counting formula for these black holes was worked out first in an inspired guess by Dijkgraaf, and Verlinde, and then justified in various ways. And it basically says that there's a nice generating functional. The coefficients d5 here, as a function of the charges, the momentum, the brane number, and the angular momentum, are given by this very explicit formula, where phi, this object here, that depends on the three chemical potentials counting the various charges, is a famous object in mathematics called the Igusa cusp form. Via the 4d5d lift, this also has an interpretation in 4-dimensional n equals 4 vacua. So there's a set of 5d black holes that correspond nicely to 4-dimensional n equals 4 BPS states as well. Now, as I mentioned, this phi is a well-known object. It's something called the Igusa cusp form. But it enjoys relations to many other reasonably famous automorphic objects. For instance, from the relation to d1, d5, it shouldn't be surprising that this object is related somehow to K3. After all, the moduli space of a 1 brane moving around in a 5 brane, well, if there's n1 branes, it would be something like the symmetric product of those K3 surfaces viewed as sigma models. So a sigma model with target sim n K3 would be some approximation. And it turns out this Igusa form can be expanded in the charge n, where the n minus first power multiplies the elliptic genus of the symmetric product of nk3 surfaces. That's not quite true. There's a correction factor, which is, again, a reasonably well-known object, something called a Jacobi form, that depends on the remaining two chemical potentials, other than Q1, Q5. So here's an expansion of this object. It looks rather complicated. P is one of the chemical potentials. It's counting the number of terms in the Mn. And here Y is the chemical potential for the angular momentum. The interpretation of this factor, the phi 10(1), is that it counts BPS states of the wrapped 5 brane with momentum on the circle and angular momentum in R4, even in the absence of ND1 branes. So that's a factor not taken into account by the symmetric product of the K3s. Now, this function, or more properly, the inverse of this function, also has an interesting role in geometry. It has an interpretation in Gromov-Witten theory as counting curves in the K3 surface where the source genus being mapped to the curve is controlled by the power of Y, and the self-intersection of the curve, where its genus in the K3, is controlled by the power of P. And that Q there is a typo. So here's a small puzzle. This function is counting one angular momentum quantum number, as was phi 10. But if you just think about the physics of a massive particle in 5 dimensions, the little group for such a particle is SO4, which has 2 SU2 factors. And so a priori, there's room for another quantum number for the other SU2 spin. Now, an appropriate function for this counting problem appeared in a paper by mathematicians Katz, Clem, and Pandey a year and a half ago about motivic Gromov-Witten theory. So they wrote down this function, where we have P still counting the charge n, but now we, in addition to the y variable, counting one angular momentum, we have u, which keeps track of the other Cartan generator of the other SU2. And again, its inverse has an interesting geometric interpretation. Now, if you inspect these functions, they probably look complicated. You get used to them quickly. It's clear that they restrict to a very, very famous function, the modular discriminant delta, when you turn off the angular chemical potentials. So phi 10(1), when you turn off the angular momentum chemical potential, or this function of Katz, Clem, Pandey, when you turn off both potentials, just become the eta function to the 24th. And these functions, too, just like the Igusa form, all enjoy a relationship to invariance of symmetric powers of the K3 surface, as you'd expect from the D1, D5 picture. So for instance, the discriminant itself, delta, has an expansion in terms of Euler characters of symmetric products of K3, just counting the most naive supersymmetric ground states of D1, D5. This is a drastic restriction of the full elliptic genus. And the other functions are somehow promotions to include more information. So phi 10(1) promotes the Euler character to something called the Hirzebruch genus. And finally, this function of Katz et al. Counts the Hodge polynomial of the symmetric powers of K3. Now, we know we can do even better than this. We know that if we go back to the intermediate step here, where we keep track of these Hirzebruch genera, we can promote the resulting object with these coefficients, with m running over the sim n K3s, to a Siegel modular form that counts black holes, to the Segusa form. So a natural question is there a similar promotion of this Hodge counting function of Katz, Clem, and Pandré-Pandé to count something else related to 5-dimensional black holes? The answer seems to be yes, and I'll work up to it in stages. So in the first step, what we'd like to do is promote this function with its extra variable to an analog of the elliptic genus with an extra variable, in the same way that the elliptic genus generalizes phi 10(1), which keeps track of only one angular momentum. This is a little subtle, because just like the full Hodge polynomial, but unlike, for instance, the Euler character, the object that we want to obtain doesn't really come from a limit of a torus partition function in a half-twisted sigma model. What I mean is that you can obtain the Hodge polynomial of a 2,2 conformal field theory with Calabi-Yau target if you want by computing a trace over the Ramon ground states, shown here, with y and u counting the powers of dz and dz bar in the cohomology. But this is not really a full torus partition function. You restrict it to ground states. You can define a similar object here, but then you have to be very careful in thinking about its invariance properties by taking a trace over what would normally give you the elliptic genus, but restricting the trace by hand to right Ramon ground states. So you have the y to the j left, q to the L naught, and a u to the j right. And when you take q to 1, that basically gives you back the Hodge polynomial. So this is our proposal for something that we would call a Hodge elliptic genus. As an example, you can just compute this thing for K3 compactification. I've given it here in terms of theta functions. For anybody who's spent too much time studying K3, the 8 times the ratios of theta 2, theta 3, and theta 4 are famously the elliptic genus of K3, computed 25, 27 years ago by Iguchi et al. There's an extra term here. There's a zero mode in this theta 1 that needs to be regulated carefully. And the additional variable u appears in this way. As expected, this object restricts to the elliptic genus when you take the new chemical potential u to 1. Now in step 2, we can second quantize this the way we did with sim n by summing over all n, and define a new function script z of 4 variables, which sums p to the n times this Hodge elliptic genus of sim n of K3. This object then clearly has some interesting properties. When you set the new chemical potential to 1, it restricts to the counting function for 3 charged black holes. When you set q to 0, it now restricts to the function of Katz, Clem, and Pandré-Pandé, which actually counts both angular momenta, but lacks the q variable of the genus. Now, BMPV black holes were originally studied in the setting where there could indeed be 2 angular momenta in 5 dimensions, and they were related to world-sheet fermion numbers in the effective string whose states you're counting by the 2 Cartan generators being f left plus f right and f left minus f right. And the solutions that were matched with microstate counts were those with the 2 angular momenta being equal. We believe that this new function script z that I've just defined captures counting of states with small inequality of the 2 angular momenta. Because of bounds on the possible values of f right in the ground state of such a supersymmetric system, the new quantum number never gets very large. It's bounded by the central charge of the CFT in which you're computing it. And so this is a small enough deviation that it does not need to be visible in macroscopic supergravity. But it seems to be visible in this function, which we believe is counting microstates. Now, my actual motivation for thinking about this problem at all came from one of these attempts to study deeper symmetry structures. The particular class of automorphic objects I've been describing here have a natural role in studies of something called Mathieu moonshine. The work of Katz, Clem, and Pandey found evidence of moonshine in their studies of the motivic-Gromov-Witten invariants. And our own work gives a more precise moonshine interpretation to the coefficients of these automorphic forms as arising from traces in a Conway moonshine module. This is work done with Chang, Duncan, and Harrison last year, but I don't have time to talk about it. Our hope is that this Hodge elliptic genus is a logical completion of this story, and its lift to this script z, the generating functional, will naturally extend this story of Mathieu moonshine. Okay, here we take a sharp turn. So what I say from here on out will be much more speculative. But I'm going to talk about some possible relations between arithmetic and BPS state counts. Okay, so let me move to a related story. Consider some elliptic curve. Here's an elliptic curve. Y squared plus y is x cubed minus x squared minus 10x minus 20. Now, you might possibly be interested in the count of points on this curve, viewed as a curve over Fp, the finite field based on the prime p. You might also not be interested in this, but number theorists tend to be interested in such objects. They're very natural in number theory. So let's suppose you count this number of points for some p, and you get n sub p. Now we define a slightly shifted number, a sub p, which is p plus 1 minus n sub p. This shift is to get rid of some sort of expected answer. If you want the expected answer was p plus 1 by some definition, and you're shifting away to get the deviation. You now extend this definition from a sub p with p prime to a sub k with general k in the following way. You define a p to the r plus 1 recursively in terms of ap and ap to the r and lower powers. And to more composite index coefficients with amn is multiplicative. So the resulting a's, if you think of them as coefficients of an object, it's a multiplicative object. The coefficients are multiplicative. Now, these definitions have been for something called primes of good reduction. The coefficient that I've defined here is modified in a simple way at primes that are primes of bad reduction. What that means in plain English is the curve could be singular. We all know how to check if it's singular over C. You can do the same thing over Fp. And when the curve is singular, viewed as a curve over Fp, the prime is of bad reduction, and you need to go through a more detailed algorithm to determine the resulting coefficient. So for the particular curve I mentioned, 11 is a prime of bad reduction. Now, if we gather the resulting coefficients, I gave you an algorithm for coefficients, together, we get some formal Q series, f of q defined by the sum of an, q to the n. And for this particular elliptic curve, I think it was first proposed by Eichler many years ago, that we find an elegant result, that f of q is the square of the eta function times the square of the eta function of 11 tau. The 11 tau is not a coincidence. That 11 is related to the fact that 11 was a prime of bad reduction. This happens to be a cusp form of weight 2, not for the full modular group, but for a congruent subgroup known as gamma naught of 11, which just means that you take the SL2Z matrices, A, B, C, D, and restrict the coefficients in appropriate ways. Now, this example is in fact a particular example of a much deeper relationship between elliptic curves and weight 2 cusp forms that follows from something called the modularity theorem, which was related to the Taniyama-Shimura conjecture, famously proved by Wiles, which basically says given an elliptic curve with the right properties and taking care of the primes appropriately and counting the solutions, you get a modular form of weight 2 that's an eigenform under Hecke operators and modular for appropriate congruent subgroup. Here's some natural questions. First, are there analogous results for modular forms associated to counting points on higher dimensional varieties? And second, and obviously this is the most important question here, do these point counts have any interesting physical interpretation, say related to the appearance of automorphic forms in various string theory BPS state counts? And this is a question I'm not the first one to consider. Certainly Candelas and his collaborators have thought about this in other contexts. Now, here's a basic result. There's a large literature trying to associate modular forms of various sorts, or more generally automorphic forms, to varieties. And basically motives or manifolds with the same structure as rigid Calabi-Yau manifolds should be modular in the sense that their point counts give automorphic forms for SL2Z or for congruent subgroups of SL2Z. If the Calabi-Yau were not rigid, the story gets richer and is less worked out. A special example occurs in d equals 2 where there's an exception. There's only one non-trivial Calabi-Yau space, K3. K3 is famously not rigid, but it turns out that K3 surfaces that are singular, that is, whose Picard number is 20 maximal, are thought to be modular as well. They're in some sense analogs of the rigid Calabi-Yaus of higher dimension. Now here's an observation about n equals 4 string vacua. I need data, and so I don't just want to take the heterotic string on T6. So I'm going to take a list of so-called CHL strings. These arise by taking heterotic on T4 times T2, or type 2 on K3 times T2, and then doing a ZP orbifold, which acts in some way on the K3 and shifts the circle. Okay, and the counting functions associated to BPS states of these models were studied in great detail with a full analog of this story of the Agusa cusp form worked out by Sen and his collaborators and Govindarajan and his collaborators some years ago. So here's a list. There are various primes P that one is orbifolding by ZPs. Here's the trivial orbifold that gives the heterotic string, and then Z2, Z3, Z5, and Z7. In the next column, I list the function whose inverse is the BPS counting function for half BPS states. It's delta for the normal model, the eta to the 24th of the 24 free bosons of the heterotic string in light cone gauge. And then you get eta products, eta to the 8th of tau times eta to the 8th of 2 tau, and so forth for the other primes, whose weights go down. And there's an associated number k here, which is the weight minus 2. Now, the inverse half BPS counting functions are shown here, but as I said, there are quarter BPS formulas for Siegel forms that count quarter BPS states. I'm not showing those. We could also look at the moduli spaces of these theories. These tend to be large spaces, so I'll look at the simplest factor in the moduli space, which is the space on which the axiodileton itself lives. So because of S duality, for heterotic on T6 or type 2 on K3 times T2, the dileton lives in a moduli space, or certainly the heterotic dileton lives in H mod SL2Z, and then that moves to other moduli in the type 2 pictures. The literal heterotic dileton is dual to, for instance, the modulus of a torus in type 2A. But for the other strings, one gets other moduli spaces. For P equals 2, the upper half plane mod gamma 1 of 2, for 3 mod gamma 1 of 3, and in general there are congruent subgroups associated to the primes that change the structure of the moduli space. I've also shown here the dimension of middle cohomology of K3 invariant under the automorphism, under the orbifold action, and it's controlled by K. It's precisely K. Here are some interesting and somewhat suggestive facts. For each of our test cases, the moduli space of the axiodileton is of genus 0. You view that space as a Riemann surface. You can compactify it appropriately. You ask what genus Riemann surface it is, and these are all spaces of genus 0. There's a standard construction associated with such moduli spaces, yielding something called a Kuga-Sato variety, that does the most obvious thing possible. Given a point in the moduli space, you can make a larger space by associating with that point some number of copies of the precise elliptic curve specified by that point in moduli space. It's sort of a tautological construction. So we've observed the following striking facts. The Kuga-Sato variety that you obtain by taking the k-fold fiber product of the elliptic curve over the axiodileton moduli space for each k is birational to a Calabi-Yau whose point counts give precisely the cusp form controlling the half BPS states for that k. Okay. In other words, for instance, in the simplest case, the half BPS counting function delta itself arises from counting points in an appropriate rigid Calabi-Yau. This Calabi-Yau is an 11-fold, which is birational to a 10-fold Kuga-Sato fiber product over the axiodileton moduli space of the heterotic string. And in fact, this manifold was found by Paranjape and Ramakrishnan, a mathematician at Caltech, a few years ago. It would be extremely interesting if this presaged a role for an auxiliary geometry whose number theoretic properties, like these point counts, govern the physics of n equals 4 string compactification. I wish I had more to say about it now, but I don't, so I'll stop my talk. Thank you.
Okay, time for questions. Very nice talk, Shamit. I have a question and a comment. So the comment is about this auxiliary geometry. In the a way, in a closely related problem where you can refine BPS states, which is actually keeping track of 2SU2 schemes. This can be reformulated mathematically as empiric BPS invariants, and they are essentially, by definition, counting points over phi over moduli spaces. So this ability to repeat the moduli space. So that's common. And the question is, in the first part of the talk where you find the correction term, which turned out to be the strict Mobius form, suppose we didn't do the computation, could we predict that it should be just Mobius form of a given weight index?
Yeah. These are great questions. Sorry. So first, thanks for your comment. And your question is a great question. One can predict, for instance, the weight of the cusp form arising in the half BPS count because it appears in a physical coupling. It's the coupling that controls the R squared plus ... term that corrects the n equals 4 Lagrangian, the first sort of non-trivial quantum correction. And that correction, just by sort of macroscopic arguments, is governed by half BPS states. The weight of the modular form appearing in a log in that correction follows from detailed properties of the n equals 4 effective action. And so one can actually predict the thing appearing there should be a cusp form on physical grounds and of a certain weight. And if you know the relevant congruence group for the axiodileton moduli space, that basically fixes the answer. I think a more detailed version of the kind of argument I just made would extend to the Jacobi forms. For the most refined object I discussed, this script Z, which is the sum of Hodge elliptic genera, we're still trying to understand from first principles its automorphic properties. We know it restricts to nice automorphic objects, but we don't have a first principles understanding of its full automorphic properties, and so we didn't compute it that way.
More questions? I can't see any.
I'm trying to explain this, but maybe just summarize this. Is your auxiliary geometry related to the whole family of magnifications of a given type with all its moduli?
If I had a very precise statement along those lines, I'd be very happy. It would still leave a lot of work, but I'd have a better understanding of the situation than I do now. It seems to be related to a fibration of a slice of the vector multiplet moduli space over the axiodileton moduli space. And the physics that selects this slice and the physics that governs the precise relationship between the automorphic form here and the actual counts, which involves an inversion that doesn't show up in the effective action since that's just a log, but which shows up in actual integers, is something I'm still trying to understand.
Do we have any idea at all, in any case, why counting points has anything to do with it? Or is it just a question of formulas that were computed and agreed?
I think for now I'll say it's a question of formulas that were computed and agreed. There are suggestive papers by Badarev years ago that get volumes of various varieties by point counts. And so one would think that literal BPS masses themselves may be related to point counts. But for this generating functional, I don't see any suggestions in earlier literature.
Thanks.
For this counting formula that you found, including the second angular momentum, is there any argument that that is independent of the coupling?
Yeah, so this is related to my statement that because the way we defined that object counting it was by this sort of artificially truncated trace, the moduli dependence of that kind of truncation is not obvious. There's no sort of Q deformation argument that says it's moduli independent. So a priori, one would guess that you could go through analogous steps as what I did here for Calabi-Yau threefolds, define some object. It may well be moduli dependent. My thinking based on the math literature is that for K3 times T2, there's a good chance that this object is moduli independent. And we see a way that we might be able to prove that using the mathematical definition of these genera, but we haven't completed the proof.
Other questions? Is there any way to formulate the Hodge elliptic genus in terms of a sigma model? Like, what does it count in the sigma model, the states of the sigma model? Is that going to be right enough, like the usual elliptic genus?
Yeah, so I wrote the closest analog I know, which is the normal elliptic genus is formulated by taking a trace of q to the L naught, q bar to the L naught bar, y to the j naught, with some -1 to the f's. And then that trace automatically, as long as the spectrum isn't continuous, restricts to right-moving ground states and gives you the elliptic genus. The analogous definition here wouldn't work to give you an index, because now you're basically counting the right-moving U1 charge, which doesn't commute with the supercharges that make the elliptic genus an invariant. So I did a brutal thing in giving the suggestive physics definition. I just truncated the right movers to remote ground states. That is a definition that you could compute point by point for a Calabi-Yau sigma model, but then the question that I was asked and that I discussed, that of invariance under deformations, is subtle, and you have to discuss it on a case-by-case basis.
So, in view of the time, maybe we should move on, so let's send Shamit.